Okay, we're recording. Hi, everybody. Welcome to Scale Machine Learning Code with Dask. My name is Nathan. I'm the host. Please feel free to direct any comments or questions to Slack. Let me introduce our speakers: Andrew Mshar, Ryan Soley, and Mike McCarty. I'm going to let them introduce themselves. So over to you guys.
So I'll go ahead first. I am Andrew Mshar. I've been with Capital One for about 2 years in the Center for Machine Learning, and I'm working on an internal library that's kind of incorporating a lot of the concepts that we'll teach here today. I'll be kind of at the end of the tutorial, so I just wanted to introduce myself first so that these guys could jump in.
Yep, and I'll quickly introduce myself too before Mike gets started. My name's Ryan. I've been working with Andrew on the same team in Capital One C4ML for, I guess it's been 3.5 years now. But yeah, mostly working on a model monitoring and logging tool called Rubicon. I've talked about a few times today, you may have seen, and also just giving a hand to the other projects that we're all working on. So yeah, take it away, Mike.
Okay, I guess that means I'm going first. So I will share my screen. Okay, can everyone see my screen okay?
Yep.
All right, thanks. So yeah, we're gonna go through a tutorial that we put together. This tutorial will start where if you've gone through the Dask tutorial before, one of the later notebooks, the Notebook 8 machine learning notebook, is kind of like at the end of the tutorial, and usually, depending on how much time we have, we usually kind of rush through that. So that's where we're actually going to start today, and just kind of give you an intro to machine learning in the PyData stack. We're going to go over a Scikit-learn example and talk about how you can use Dask-ml to scale that. And then what we'll do is we're going to walk through a couple of other examples and have some exercises throughout, and then kind of like towards the end, we're going to have a kind of a little project that kind of walks you through how to start to build and extend Dask-ml in order to build your own custom estimators. And so that's kind of the goal for today. This is the repo that we're working out of. There's also a binder link that we've set up here. If you want, you're welcome to spin up a local instance on your laptop as well, or just use the binder link. We sent these, I believe we sent these instructions out ahead of time. And so if you've gotten those, if you've not, please go ahead and do that now. You're going to clone the repo if you're going to run locally, and there's instructions on how to spin up your environment, and then run your own local Jupyter server, so we can walk through this tutorial. I can't remember, were we going to give folks time to do that, or are we going to just kind of move on and dive in while folks are setting up their environment? Does anybody not have an environment set up yet? Hopefully, we also want this to be interactive too, so feel free to if you're comfortable going on camera and chatting with us, we'd like that too, or just unmute. But does anybody want to wait maybe 5 minutes to set stuff up, or are we good to go?
I'm personally good setting it up as you go.
Okay, thank you for chiming in. Appreciate that. All right, I'm going to assume everyone agrees with you. We'll just move on and we'll dive in. Okay, so I'm running this locally. And we'll start with, like I said, the intro. One real quick thing I'll note. We also have the overview, first notebook from the Dask tutorial. I realize that there's some stuff we didn't clean up here. But basically, walk you through the structure of these notebooks real quick. So we're generally going to work through different examples. We'll get to a point where you'll need to enter some code. This is a Jupyter notebook, so you can just type in code here like you normally would. And then hit either Shift Enter, or you can just click Run to run the cell, and you get the output. When you see the ellipses, that's usually at the end of an exercise. That's going to be the answer. So if you want to cheat and move ahead, you can just click on the ellipses to expand that cell and look at the answer and run it. Or if you want to compare your answer with what we've at least put in here, you can check that out. So that's the notebook, kind of like in the tutorial structure and how we'll go through this. So now I'll move into the actual notebook. So like I said, this is the last notebook actually in the Dask tutorial. We're going to pick up here, and then we're going to kind of continue on. And this is the first time we've given this tutorial, so would love your feedback. We're looking forward to giving this and hopefully contributing this to the main Dask org eventually to build out a more comprehensive machine learning tutorial. So what we start with in Dask-ml is we kind of have two different types of scaling that we're trying to address with Dask-ml. There's the model size versus the data size. So usually the model size is bound by the CPU. The data size, of course, is bound by the amount of memory you have on your system or cluster. And there's this general sweet spot in the lower left corner where all of your data fits into memory and you can do your computation on a single machine. And that's kind of where kind of classical machine learning or scikit-learn kind of means to address, or the in-memory, the in-core PyData stack, right? And there are various ways as you go up on the computational complexity here and become CPU bound of overcoming that. That is kind of baked into scikit-learn through joblib and through threading and parallelism there. But sometimes you reach some limits there in terms of what you can, well, many times you'll reach limits there in terms of what you can do on a single machine, and you want to scale it to multiple machines. So Dask-ml has some utilities for doing that, some integration with joblib to be able to actually scale out across a Dask cluster for the situations where all of your data fits in the memory on a single machine, and you just need to kind of scale out your kind of these embarrassingly parallel problems, right? And then on the data size, Dask-ml provides some scikit-learn-like estimators that deal with Dask collections for those cases where you actually need to scale your data out across a cluster and be able to have like a Dask array and pass that into an estimator for training. So those are kind of the two dimensions of scale that we get here that we talk about with Dask-ml. Before we get too far into that, we're going to kind of do a quick primer on scikit-learn so that we're all kind of on the same page here in terms of what we're talking about when we're using the scikit-learn API. Within the scikit-learn API, we have a number of different estimators. There are different actually types of estimators that do various things, whether they're transforming, scaling, or training a model, or scoring a model. And so those are different kind of collections that are in the API. They typically, the estimators that are training a model will implement a fit method. You'll pass in X and Y's, and that will change the state of the internal estimator and train the model, and then you can score and things like that. So we're going to walk through an example of what that workflow looks like, just to kind of get our appetite kind of primed here. So I'm going to import a data generator. We're actually going to use data generators a lot in this tutorial. These are baked into scikit-learn. There's also some in Dask-ml that return Dask collections. So you can say number of samples, number of features, all kinds of other parameters on this. Whether there's also a make regressor data, and this just returns a NumPy array. And also returns your targets as well. So those are features in the X array, and then our targets we're going to try to predict on our Ys, and we'll use that for training. And there are various algorithms within Scikit-learn. Here we're going to use a support vector classifier. And what you'll typically do is you'll initialize that, that estimator and then call fit on it and pass in your X and Y. And so this is going to invoke training. And usually that changes the state of the estimator. So there, in this case, there are support vectors. We can look at those. We can look at all kinds of things within whatever that particular estimator has internally that we can access. And then, of course, we can score typically you would score on new data. And we'll get into all that on splitting and whatnot later. Like I showed whenever I created this estimator, there are various hyperparameters that you can pass in. And that changes effectively the way in which the estimator will be trained. And so I just create that estimator from those different hyperparameters. I call fit on that same data, and I can get different results from that. I believe these scores are different now. So here I've effectively made my model worse by adjusting the hyperparameters. So one of the things that you're going to do in Scikit-learn with machine learning is called hyperparameter optimization. That's where we want to try out different hyperparameters that we're going to pass into this estimator and then fit on our data and then score it and see which model is going to be the best in terms of performance based on these different hyperparameters. Same data set, different hyperparameters. One of the tools we use, grid search, CV. The way that works is you create your estimator, you specify this parameter grid, you pass that estimator into grid search along with that parameter grid and some other parameters that we'll get into later. You call fit, that same interface on the X and Y, and that's going to actually train multiple estimators with different combinations of those hyperparameters that we passed in. And you can also specify that scoring function. There's a default that's going to use here. And this is going to perform 8 fits, and we'll let that run. Feel free to ask any questions if anybody has them. So we're kind of feeling the performance here, right? You know, as we're running this, and we're going to talk about how we can improve that. Okay, so that's done. Took about a little over a minute, and we can get the best parameters as well as that best score to figure out which one of the the combination of those parameters we can use to get the best model possible for this data set. All right, so Scikit-learn actually has a mechanism built into it for parallelism here. Using threading, we can pass in this n jobs parameter. If you pass -1 into that, that's going to tell Scikit-learn to tell joblib to use all the available cores on this machine. And so now we're going to do 8 fits in parallel on this one machine. All right, so a little bit faster. And then let's see that we got the same results. Yep. Same score, same set of hyperparameters. So it turns out the Dask team has done some work with the JobLib team to add support for Dask in JobLib. And so what I can do is create a local Dask cluster. And so that's what this cell is going to do. And returning the client, we don't have to watch that, but we can. Might as well. We'll open that up. And then get this so you can see it. Okay. And so now I'm going to use a slightly larger parameter grid. You can uncomment some of this if you want this to run a little bit longer. You're still going to pass in njobs -1 on the grid search. But whenever you go to run fit, you can use a context manager. We're also importing JobLib and specify Dask as your parallel backend. You can then also scatter the X and Ys out onto the Dask cluster. And so what this is going to do is this is the case where, all of our data fits into memory on a single system, but we're going to scale out across a Dask cluster. We can take those X's and Y's and scatter them out across the Dask cluster. And then whenever we call fit, for each fit, they'll run locally on those workers and have access to the X's and Y's. And so now we're going to do even more fits on our Dask cluster. And we can see the dashboard light up and all that good stuff.
Hey, Mike, this is a stupid question, but how did you get the dashboard panel split like that?
I am using Vivaldi for my browser, which has a tile feature, which is great for these situations.
Yeah, it looks really slick.
Thanks. There's also, I think we set up, I don't know if we set up the Dask Live extension that you can use, but this is easier just to spin them up. Rather than, that way you don't have to watch me fumble around with Jupyter widgets. We're waiting on that to finish. I'm gonna get some more Zoom stuff up so I can see who all's here. All right, I might. I think I know. I think Zoom might be making my computer run a little slow right now. Not too bad.
Hey, Mike, while we're waiting on that, there's a question in the chat asking, when you use scatter, does it only run fit on a partition of data, or does it consolidate the results from all partial fits?
Yeah, that's a good question. So in this case, what I'm scattering is not a Dask collection. It's just a NumPy array. So that NumPy array is going to be scattered across all the workers. So each worker will have a copy of the entire data set. And we'll get in. So go ahead.
Do you know why there's like an underscore after best score and best params? Like, is there, I'm just kind of trying to understand like the convention for scikit-learn.
Yeah, that's the Python convention is to have underscores for in front of attributes, class attributes, so they're meant to be private, but in Python, everything's public. So there's that convention, and this is just the convention that scikit-learn has adopted for. Typically, you'll see that as attributes on a class that mutate in some way whenever you fit.
Oh, okay, cool. Thanks.
And Mike, excuse me, and Mike, one more follow-up in the chat about how scatter works if the data don't fit into memory on the workers. Can you talk a little bit about that?
Yeah, you're going to run into a memory error, and that's a case where you're going to need a Dask collection. So there you're getting up here. Let me go back up to this graph. So that's a case where you're getting into this like upper right quadrant of this graph where you're computationally bound and you're memory bound. And so you're going to need a Dask collection.
And for a Dask newbie, that Dask collection, is that like lazily loaded? Is that why it's like out of core? Okay.
Well, it's lazily loaded, it's out of core, but in the case of a distributed, so it depends. Are you going to run this on a distributed cluster or not? If you're running with a local cluster like we are here, then you're going to be dependent on the lazy evaluation. We actually have an example of that at the end of this notebook. I'm not going to run it because it's going to make my machine run even slower. You all can run it if you want, but it's an example of taking advantage of lazy loading on a Dask collection, passing that into a Dask-ml estimator, and taking advantage of out-of-core processing on a local system.
Just an additional call out there. That's a really good question, and it's something that I'd encourage everyone here to kind of think more about. One thing that's awesome about Dask is in a lot of ways, you take your data, make it a Dask data frame, which seems to be like a pandas data frame, and then you can run something with, for example, a Dask XGBoost estimator, and it just runs against stuff that wouldn't fit into memory. It's kind of magical. But like Mike is talking about with that graph, it's important to understand that if you are in the upper right, it can't scale infinitely. You kind of have to make a trade-off there. So it's, if you are, working out of memory, if you're not fitting in memory, there's communication overhead between your processing. And if you're processing very fast, you might be generating extra memory. So it's important to kind of understand that trade-off. I just kind of want to call that out as something to think about, because it's easy to get something small to work. And then when you run into something bigger and you're running into a real workload, it's like, wait, why isn't this working magically like it did for this other example? So just something to keep in mind and to dig a little deeper on after this.
That's a great call out, Andrew. Okay, so that finished. So we essentially searched on more hyperparameters while broadcasting over Zoom, and found a slightly better model, because we noticed our score has improved here as a result of just searching more hyperparameters. So this is the old score, and then the new score with more hyperparameters. And I don't know about y'all in the domain that you're working in, but for us, like minuscule improvements in score means real dollars in revenue for us. So like this is totally worth it. We've actually, this is a very like minute example, but we've done this a lot on our team, internally within our company, just by like adding GPUs and expanding our hyperparameter search and using Dask for parallel hyperparameter tuning, or just building our own some of our own hyperparameter tuning, essentially searching more hyperparameters and finding better models. Okay, I'm going to restart my kernel real quick so that things run smoother here. Why Zoom is being so pesky for me. And regenerate data real quick. And restart my cluster. Okay. So another thing you can do that we wanted to point out is you don't have to you don't necessarily have to use Dask for training. You can train on a small data set if you want, or an in-memory data set. And so here we're going to do another grid search. Oops. I was already starting my kernel. Oh, and grid search is not defined. Okay. Wow, my system is running really slow. Okay. So you can fit on a data set that is just a NumPy array in this case, fits into memory on a local system. This is just regular scikit-learn. And then I can take that data set and in this case, we're just going to kind of replicate it to create a Dask collection and create a larger amount of data. Let's run that, and you get these nice widgets with Dask that show you, what the chunks look like and the total amount of memory. So this is a Dask collection now I've created, and then I can use that Dask collection on that that grid search object that I created, the Scikit-learn grid search, and train with it, and make predictions with that Dask array. So that's really nice that you can do that. And then this next example that I'm definitely not going to run today, but we'll walk through real quick, is how to train on large data sets. So I'm going to pull in a bunch of Dask stuff, and then another data generator from Scikit-learn. We're going to do k-means here, so we're going to make a blob of data, and then we're going to replicate that a lot to build up a larger than memory data set. I actually am going to run some of this real quick just to show you what this looks like in terms of the amount of data. It won't actually run. So whenever I run this, whenever you call compute on or persist on this data set or do something with it with a Dask estimator, it's going to end up generating a lot more data than what I have on this laptop. It's going to generate, in this case, 17.8 gigs of data. But that's lazily loaded because it's Dask. I'm running this on a local cluster. I can then import a Dask-ml estimator, k-means, and call fit on that. That'll take a little while to run because it's a lot of data, but it's going to run. If you were to try to do this on an NumPy array, you would just get an out of memory error. But we can actually do this with Dask on a local system or on a cluster. Okay. Any questions about that before we move on to the next notebook? Okay. Good question. Are all the scikit-learn estimators defined in Dask-ml cluster? No. But if there's one missing that you would like, please open an issue. We'd love to hear about it. We typically don't implement all of them unless they're needed. All right. I'm going to stop sharing my screen actually because my computer is really misbehaving. Andrew or Ryan, do you mind sharing your screen? And I don't mind talking, but I think it might go smoother.
Yeah, sure. Notebook 2, right?
That's right. Thank you.
Yep.
I have a quick question, actually. When I run fit on k-means, I'm getting a warning that says full garbage collections took 14% of CPU time. Is that common or should that be ignored?
So this is a warning that's coming out?
Yeah, this is like a warning from distributed utils when I call clf.fit on the for the k-means. Yeah.
Are you running this locally?
Yeah, correct. So
yeah. So go ahead.
Oh yeah, sorry, you go ahead.
So I was just going to say, yeah, so there are parameters that you can set and limits in number of workers on like the local cluster that you're basically running into those thresholds on your Dask cluster because it's running locally. You actually might get a more consistent experience if you run this on the binder notebook.
Gotcha.
But essentially what's going on is it's running into limitations of the Dask cluster and the defaults that are used whenever you spin up a local cluster.
Okay, got it, thanks.
I just have a quick question. I think you already spoke about it. So basically I have an algorithm that I train on a small data, which is easy to train. But now when I'm trying to predict, it's like really, really large data. It's like takes hours and hours. And that's what post fit or something, that's what it is for?
That was the predict example was showing you.
Okay, so that
would be something right? Like that.
So I can train like a scikit-learn, classic scikit-learn model, and then when to prediction, I basically use post fit.
You would use predict, but or predict proba, but you could pass it a Dask collection.
Okay, then it's going to be faster.
Well, so in that case, what we were doing was we were predicting on larger than memory data sets. It's not necessarily going to be faster.
Wow. I mean, I got access to multiple cluster data. I just want to be able to scale to, more than one machine during the prediction stage.
That's right. Yeah.
Okay.
I have also a question. I actually typed my question in the chat, but I think you haven't seen that. It's about those algorithms that are not implemented in Dask-ml, for example, isolation forest. And for example, it doesn't get as input a Dask data frame, right? So for such problems, what is your suggestion? So I know, for example, this, it doesn't work, isolation force, it doesn't work on the whole data set anyway. It just uses sampling. And for each estimator, it just uses a sample of data. But at first it needs to see the whole data to just build those samples out of it. And because it doesn't get the data frame, right, Dask data frame as an input, then we cannot even read data into a data frame and then pass it to the fit in isolation forest. Do you have any suggestion for this type of problem?
Yeah, I'm not familiar with isolation forest. I think it's, so if it's not implemented in, like in general, if the estimator isn't implemented in Dask-ml, then it either hasn't been asked for yet, or there's like some limitations, like maybe the algorithm doesn't scale to a distributed computing framework, right?
Yeah.
And so in the case of like k-means, for example, there's actually like a different, it's a different, or no, I'm sorry, it was spectral clustering. There's actually a different implementation.
Right.
And so sometimes that's what you have to do, is you have to go like to the research and figure out, well, what's the alternative implementation here that would you know, work on a distributed system, and
rewrite.
then rewrite it. Yeah.
Yeah, because that's actually a problem that I'm just dealing with right now. That I thought actually maybe that post fit, parallel post fit might help, but still, I don't know if just take a sample of the data, read data into data frame, and then take a sample and just give that sample to the fit to just build the model, and then use parallel post fit to just, you know, predict the scores for all the remaining data points, something like that. I'm not sure about the accuracy, but this is just one of the, you know, just workarounds that I can think of. But as you say, I think that the right way to do that is to just think of rewriting the whole algorithm itself.
Mm-hmm. Yeah, and we've had to do that before. So it just depends on the algorithm. I'm looking, you can also check the issue tracker. I don't see anything on it.
Yeah, sure.
But yeah, that's a good question. So sometimes in those situations, this next example might actually help, just depending on the algorithm. So there's this thing in Scikit-learn called partial fit. And in cases where you can, when you don't need the entire data set, or maybe you just want to fit chunk-wise, you know, across a large data set, and you're just fitting multiple times, calling fit on different X's and Y's, and over time that's improving the accuracy of the model. There's this kind of API in Scikit-learn called partial fit, and Dask-ml is actually implemented an incremental fit estimator, or meta estimator, that takes another Scikit-learn estimator that implements this partial fit and allows it to work on Dask collections. Now, oh, go ahead.
Yeah, I looked at that as well, but you know, partial fit should have been Scikit-learn should, I mean, that model should have partial fit implemented. And for example, for isolation forest, there is no partial fit. I think that the nature of the algorithm is somehow that it might not be full. I'm not sure, but yeah, I've also looked at that. Maybe I should look at that again. Maybe I can find something interesting. But yeah, thank you.
Yeah, absolutely. We actually ran into a similar issue with XGBoost. We did a lot of work with XGBoost, and it doesn't implement the partial fit API. It's possible to do a partial fit on a GBM, but it hasn't been implemented, so we can't use it here. Maybe someday. So Ryan, if you don't mind scrolling down, we'll kind of work through this notebook now. This is just another example of that same graph I showed before. We can scroll past that. All right, so let's create a desk cluster, this time with 4 workers. And now what we're going to do is we're going to use, we were using make classification before, but you'll notice here we're using Dask-ml's make classification rather than the Scikit-learn implementation. The main difference here is that this is going to return a Dask array rather than a NumPy array, and you can specify the number of chunks you want for that. And so that's our training data. There is a train test split that's implemented in Dask-ml, so we wanted to show that off here. Primary difference is it operates on a Dask collection, in this case, a Dask array. And so we're able to split our data and have like a holdout data set for testing. We're calling persist here because we just want to go ahead and persist. Dask is lazy. We want to go ahead and persist the data on our cluster so that we can then reuse that and not have to rerun all the generation and the splitting. In this example, we're going to have some pre-computed classes, so we'll pull those out, and we're going to use the SGD classifier on that. This is just the scikit-learn version, and then but it implements the partial fit API, and so we'll pass that estimator into Dask-ml's incremental wrapper and tell it what scoring metric we want to use. And so we have now our Dask-ml incremental estimator. We can call fit on that, and we'll see the Dask cluster light up, and we can score. And this is our score, but now we can actually like pass over the data many times, call multiple fits, and improve our score. So that's what we're going to do in the next example down here. Let's go ahead and run that. So we're going to fit 10 times, and we'll see our scores getting better as we're training on more data. And now we can test out our predictions on our chest holdout. That's also a Dask collection. Hooray. And so that's another example of how we can use Dask-ml for incremental training. All right, so if there are no, wait, maybe there is a question. It's the same Dask collection, but we'll train, if you scroll back up. I'm sorry, the question is, are we passing the same data or new data to partial fit?
Scroll further up than this, or?
Nope, so right there. So we're passing the same Dask collection, but it's implementing partial fit. And so it is passing over the same data, but the scores are getting a little bit better because we're seeing different parts of the data each time we call partial fit. Okay, so that was meant to kind of get your feet wet a little bit with Dask-ml and the capabilities. We're going to go through, Ryan's going to take us, I think Ryan's going to take us through some more hyperparameter tuning, some other features, and he's got some exercises for us. And then when Andrew jumps in, we'll do the project at the end.
Cool, yeah, so I'm going to quickly go through a few things here to make sure Andrew has enough time to get through his project. Sorry, you guys, okay, cool. I wasn't sure if you could hear me. My thing wasn't, Zoom looked like it wasn't working, but I think I'm good. Okay, so basically what I'm going to show you guys are a few, so Mike was showing you how to use Dask with existing Scikit-learn things for the most part and existing other libraries. So these next few examples are just going to show a little more of the built-ins to Dask-ml that improve on those existing ones, more so than just by distributing the existing stuff. So we're going to take a little bit of a deeper dive into hyperparameter optimization, which Mike touched on with the grid search examples. So, you know, this first part here just has a little more info on that. Mike pretty much covered it all. But the important thing to call out is that, you know, like he just said in that last one, we have this partial fit method and another warm start one. And these are normal scikit-learn things that are present on a good amount of existing estimators that Dask is able to take advantage of to, to provide optimizations for out of memory or data. So in this particular notebook, we're going to take a look through the Hyperband search CV, which is, similar to grid search, accomplishes the same thing in terms of finding the best hyperparameters for you. So just to start off here, I'm going to set up a cluster and create some sample data. So for this example, it's going to be a classifier. So we're going to, get some data here that we want to differentiate between this outer and inner ring. And then we're just going to add these dimensions here just to get everything set up and ready to go for Dask. So this is where we start getting into things. Right now, we're still just using Scikit-learn to train, test, and split our data. This all currently fits into my local memory. And if we just take a look, we can see that we have our train and test set. Not very big. But what is fairly big on this, much bigger than the example that Mike showed, is this parameter search grid. So we are going to be taking a look through a lot more different possibilities, and hopefully it takes less time unless Zoom wants to bog down my laptop too. But sorry, let me get through that. So, and just to call out, we're going to use just a regular Scikit-learn classifier here on the MLP classifier. So the important thing about the Hyperband search CV in relation to the grid search is that it provides a few methods for early stopping. So essentially, it's trying to intelligently, prune out bad solutions before it has to use up all the compute to actually finish them. So it's just a few more optimizations on top of the existing grid search. And again, this is, working in parallel across with your data. However, it can take in Dask and Dask data sets. Quickly, we need to set up a few input parameters that aren't hyperparameters. There are a few things that we know are going to be the best for this this particular model based on just based on our data itself. So I don't want to dive into the weeds here on this, but these are just a few values based on the length of our data set that will pass into our estimator before we actually start looking for other hyperparameters. So these ones we know are good, so we're just going to set them to the proper value. Now, here again, we're going to actually make some Dask arrays for our inputs. Are we? There we go. And we're going to create our Hyperband search CV. So this is just we're giving it the model and the parameters, which is very similar to what you saw with the grid search. And these are just those few extra parameters that we know what they need to be. So we're just going to pass them in as they are. So before we even do anything, there's some metadata that's generated, and we're able to tell exactly how many calls that this is going to make in the worst case. So essentially, this is saying at most we're going to have 26 partial fit calls here, and then this is just some more data about how it's going to do those and what it's looking for. And now we are finally ready to perform the computation. So here we're going to fit it just like we would, we're calling fit with our training, just like we would do on the regular grid search. And now we're going to start seeing some partial fits happen here. As this goes, it's, under the hood, this is throwing out bad, bad solutions before it even gets to the point where it goes all the way through all the different possibilities. And as you can see, this is already finished, and we've already got our results. Now, this is where I want to take a second to do our first little exercise. So one thing to point out here is that this search CV follows the Scikit-learn API. So if you're familiar with Scikit-learn, it should be very easy to access any of the metadata that was produced by running that. So just quickly here, if you want to try and pull off the best score estimator and parameters, you can give it a shot as an example. If you're not familiar with Scikit-learn, you probably don't know how to do it, so feel free to take a look at the solutions. But yeah, I'll give everyone a couple seconds here to play around with that, and ask any questions if anyone has anything so far.
Quick question. So you're using an MLP classifier. Could you do something similar with like a PyTorch model for an image classification problem too, or would that look a little bit different? I guess the input data would look different, but is the general workflow the same?
I would imagine. I'm not 100% sure. I don't have enough knowledge on the space. I don't know if Mike or Andrew can chime in, but I would imagine it would at least be similar.
Yeah, I'm actually not sure for PyTorch because I don't know if that works with Scikit-learn. That's the only question I have. You can definitely do other estimators from Scikit-learn, but I don't know how PyTorch interacts with it. Mike, do you know?
I don't think Mike's here. Oh, is he?
No, I was just gonna say, I think that Scorch, you can use Scorch to be a wrapper around PyTorch, I think. I haven't done it, but that's my understanding.
Yeah, I mean, if you can make it fit the Scikit-learn estimator specification, then it should work.
Cool, thanks.
Yep. All right, so I'm just going to show these quick little solutions here. So we're really just pulling off these metadata attributes. So our best score here, our best estimator, and our best parameters. So this, should all look very similar to the grid search example, except we saw this time we searched a much larger parameter space, found 3 parameters we're interested in instead of just 1 in a fraction of the time. And again, just to really drive home the point, it's got all the same features that you could get off of a regular scikit-learn estimator. We can predict using Dask data sets to get our predictions. And again, it has this special history, actually. It has some few additional attributes too, which are pretty cool, just to show the different ways that it arrived at its final scoring. I'm going to skip over this exercise for the sake of time because what Andrew wants to show at the end encompasses a lot of the same things. So I'm going to hop over to this next one. Actually, let me shut that cluster down. All right, I'm going to hop over to this XGBoost notebook and show you how the XGBoost algorithm plays nicely with Dask and Dask-ml. So if you're not familiar with this, honestly, I'm not the most familiar with XGBoost either. I know a lot about how it plays nicely with Dask, but it's a good algorithm. It's used very frequently across many different, different frameworks for actually running it. So yeah, well, I'm just going to dive in here. So set up a cluster and create some data. This is same stuff we've seen. Just want to call out we're using the Dask-ml make classification. So this input data set is a Dask data set. Again, nothing too big, definitely fits in memory on my computer. And again, we're just going to split this data for testing and training using Dask-ml yet again. So that, as you can see, nothing actually executed there. That's all lazily evaluated before we pass it into XGBoost. So we're just going to import directly from the XGBoost library. Dask is actually, they have integrated the Dask solution directly into their library and provided like first-class support for it. So that's been super cool. There is an XGBoost Dask project out there that you may have seen and used before. I believe that this is the way to do it now. I don't think people should still be using that old one. If anyone knows for sure, you can chime in. But yeah,
that's correct.
So
Ryan. So
cool.
Dask XGBoost has been deprecated, and all of the functionality is now in XGBoost.dask. There might be 1 or 2 very small things that they haven't, but they've been doing a good job of upgrading it the last few releases of XGBoost. So yeah, do stick with XGBoost.dask.
Awesome. Yeah, and then big picture from here to the end really is just to point out that all of this is exactly the same. You can do everything the same way on a normal XGBoost object that you could on this one that you can pass Dask inputs to. So I'm going to train it with the standard train method. We're diving into this Dask submodule. So, if you weren't using Dask data frames effectively, you should just be able to get rid of this and use the same code. So this is just our standard XGBoost booster. It's not even like a Dask subclass for this. It's just our standard object that we were able to create out of that. And from there, we can do all the normal things we'd be able to do. So we can plot our feature importance just with a normal, with XGBoost normal plotting method and just passing it in that booster. And we can even do more complex things. So again, predicting. If you have your Dask data sets, you're just passing in the client. I guess that's one thing I should call out. That is the one different. You do need to pass the client around in this instance to these XGBoost ones. But beyond that and this, it should all be pretty much the same. So we can quickly calculate our ROC curve and plot that. Here we see Dask doing some stuff. Maybe not quickly. But yeah, this is finally evaluating, pulling the data in as it needs it. And there we go. So yeah, big point of these last 2 notebooks is really to show that there are solutions out. If there are solutions out there to integrate Dask into some popular algorithms, if there's something you're using, that isn't integrated with Dask, take a look around. It could be out there. And then before I pass it over to Andrew, I just want to go through one last notebook here. And this is just going to go a little more in depth on the post prediction that Mike talked about at the end of his piece. So let me quickly start up the client again and grab another data set. So this classification, again, we're going to train on in-memory data. So this is a Scikit-learn data, or this is a classification coming from Scikit-learn. So these are our standard NumPy arrays. From those, I'm going to create some bigger data using Dask. So I'm going to use the Dask arrays concatenate function to just make a bunch of copies of the X and Y train data. So now we have a set of NumPy arrays for our in-memory data and our Dask data frame, or our Dask arrays, sorry, for predicting on. And pretty much like Mike showed, we're going to just define our original scikit-learn estimator and then just wrap it in our parallel post fit. So again, very simple way of extending existing estimators in order to provide a little more Dask support. What Andrew's about to show next is a lot more custom version of what's happening here. So, this is very there are things that parallel post fit expects of this estimator so that it works properly. And I won't dive into the weeds there, but as we can see, this nicely just works. So our fit here now, our classifiers fit takes in our scikit-learn data here to fit our NumPy arrays to fit. And then for one quick example here, why don't you guys try and score that data or predict on it? I'm sorry. So this should be exactly the same. You should be able to use that one classifier and call predict on it, but this time passing it your Dask data should give you no problems and should score that large data set using the same exact estimator. So again, that's just a quick one. Like I said, all we're doing is calling predict, but this time we're using our Dask data frame as the input and getting a Dask array as the output. So essentially what parallel post fit here is doing is creating an estimator for us where the fit takes in NumPy arrays generated from scikit-learn, and the predict is giving us or is able to take in Dask arrays. So this gives us some flexibility with our estimators in terms of being able to train them on small data sets and then really, predict on them in more productionalized like environments. But sometimes, this little wrapper here isn't quite enough to accomplish everything you're trying to accomplish. So that's why I'm going to hand it over to Andrew now to dig into, providing a lot more customizations to estimators in order to really harness the power of Dask and really be able to do things like this, where you're passing different types of data in and out of your models. So with that, I will stop sharing and let Andrew take over. And of course, if anyone has any questions before Andrew starts, feel free. I see there's just one in the chat. I think Andrew took care of it, right?
Yeah, I just took care of that one. And then I just wanted to ask, we're okay on time. I just want to check if folks want just a few minute break before we dive into the last section for the last 25, 30 minutes. Just put a reaction up if you want a break. And if there are enough of them, we'll take a quick break. And if not, we'll just go right ahead. Got one vote for a break. Anyone else? Two, three. Okay, we'll take a quick break. We'll come back at 1:05, so in 4 minutes. And in the meantime, if folks do have questions, feel free to ask Ryan, or just ask away, and we'll answer.
Hey, just a quick one. So is there a plan, or is there some plan or something going on to integrate Dask inside the Scikit-learn as the XGBoost folks have done it, right? So you just pass in the client, you don't have to worry about.
No, I think the idea is to keep them separate. So Scikit-learn being the implementation for data that can fit into memory, and then Dask being its own project that, or I should say Dask-ml being the project that kind of mirrors that. And it's similar to Dask proper with data frame, right? So Pandas is its own project, and then data frame kind of mirrors that. So I think that's the idea, is to keep them separate. But re-implement and kind of follow the lead for the mirror project.
I had a quick question. So you had the third notebook was hyperparameter optimization, fourth notebook was XGBoost. Like, how much of a lift is it to kind of combine those two to do like a hyperparameter sweep over, XGBoosted models?
We're going to do that next.
Awesome. Okay, cool. I'll hold on.
I like it though. I like getting ahead of it. It's good. I'm actually going to step away just for a minute to go grab some water, and then when I get back, we'll get started with that next one.
I just want to say that was a great question.
Okay, I'm going to go ahead and share my screen, and we'll get started here. Can everyone see my screen?
Yep.
Great. Okay, so I know you guys are excited to write some code, but I want to talk for just a couple minutes first to give kind of an idea, or I should say a motivation for why we want to design things the way that we're going to, and talk a little bit about the advantages we get from doing so. So to start, we have this example that's straight out of the Scikit-learn docs. Just a small pipeline with loading the digits data set that you may be familiar with. We're going to run principal component analysis on it and a logistic regression. We'll build a pipeline using those two steps. And then we'll run grid search to find our best estimator out of that pipeline. So that's the example. Now, let's say this is something we really want to do, that we really need to find the best model here. But in the real world, what ends up happening is you kind of need some preparation steps. You need a little something before this. You might build in some other stuff. So how does that look? Well, if we look at the next cell here, this is something you might see a data scientist do who's just trying to figure out what's going on. They get told, okay, we need to mutate the data, whether that's filter out some data or drop some columns or drop some rows. We have to do something, then we can do our analysis. Okay, so we break it up. We do PCA logistic regression. We define this mutate function, and then we call that. It's a little manual, so you can see why this probably isn't a good idea long term. If a data scientist does that, that's perfectly fine. Get the answer kind of as quick as you can. But when you want to share this across an organization, or you're looking to scale with Dask, like move to a different way to process, this can get out of hand kind of quickly. So let's look into some, kind of best practices for software development. And what you might see here is you start building out these classes. And this is good, right? We're using some good software design principles to build these classes. We're isolating some of the functionality, whether it's loading data from the mutation from the model build. So it's good. You're following some best practices here, and this isn't necessarily bad code, but I want to advocate for a different way to do this, because what ends up happening here is, again, when you try to scale with, move to something like Dask or Rapids or another package on top of Scikit-learn, you'll end up building out more classes, you'll end up building out more of this boilerplate code, and you can fall into a really bad spot. So I'd advocate instead following the Scikit-learn API directly. If you're not entirely familiar with how to do this, I'll provide some links in the docs, or links to the docs about kind of how to get started and how to make sure you're following it. But the advantage here you can see is we didn't have to break up the pipeline. We're able to implement this mutate step as a transformer in Scikit-learn lingo. And in this way, we can just put it in the middle of the pipeline. The advantages here are twofold, or I should say two major advantages. The first is, as you'll see, when we try to scale using Dask, we're able to do it pretty easily, very little code. That's a huge advantage. The second one is working across teams in an organization. If you're working on this part of code and someone else is working on another part, if you're both using the Scikit-learn API, you don't have to worry about or edit each other's code or have any dependencies in code between each other. You can kind of just slot these things in. That's kind of how the Scikit-learn API is built. One good example from our work at Capital One, we're developing a library that's more centered on model building and model training. There's some other libraries, for example, one that does data cleaning. That's the specialty there. We've been able to import and just use their transformers with our code without having to, request any changes from them, without having to change our stuff, because we both adhere to the Scikit-learn API. Some other lessons we've learned along the way. So as I said, this link, if you're not super familiar with the Scikit-learn API and how it's designed and how you can design with it, we'll go through some of that. But this is a great link to how to do that, especially look at the check estimator is something you can import, and so that'll allow you to make sure you're not breaking functionality with Scikit-learn. And in fact, if you have a CI server set up, you can build that into some tests to make sure that someone else on your team or you in the future doesn't accidentally break that functionality. So that's a great link. One thing that we've found ourselves when doing this kind of scaling work, when it comes to the algorithms, so for example, XGBoost, Dask XGBoost, these kinds of things, we favor using the array-like data structures, so NumPy, Dask array, or like a CUDA array. When we get closer to that step, the downside to this is then you don't have the data frame operations like group by and things like that. But the way we solve that is moving that earlier in the process. So making that a transformer, for example, before we operate on it. But just something we found that the array-like interfaces or data structures are more consistent across the those processing operations for us. These last four are all straight from the Dask-ml contribution conventions, and definitely review these. These are pretty good. And it's what the Dask-ml stuff does. So if you're unsure of why it's doing what it's doing, you can see here. The first is just that whenever you run fit, whenever you train your model, the output should not be a Dask collection. It should be concrete, so a data frame, an array, and not a Dask type. The second one is, to the extent possible, support all of these. So, and this kind of goes hand in hand with the last one, which is whatever you're getting in from your user, as long as we're not talking about a fit, that first rule there, you should give back something equivalent. So if you're getting a Dask array, give them a Dask array. If you're getting a Pandas data frame, give back a Pandas data frame. And then the third one here, or the second from the bottom, is limiting your operations. So if possible, transformers should accept a columns keyword so that you're not operating over the entire data frame if you only want to operate on something smaller. We've actually found something very similar, which is both in terms of transformers and estimators, making sure that we accept the things that we accept are smaller bits of data. So for example, if we're, and give back. So for example, if we're, a lot of times you'll see X and Y. So X being all of your features, Y being your labels, targets, what have you. Giving back just the predictions or just the score or just the object, not giving back that entire data frame and not mashing those together. Because again, when you're scaling with Dask, the idea is to be using large bits of data, and there's no reason to pass back the feature data set if it's not used in the next step, if it's not a thing that's needed. So trying to minimize the data you're passing around there. Okay, so let's get into kind of designing these things. So the first two steps here will look pretty familiar. So we're going to do both Scikit-learn's make classification and a Dask version. So we'll have both a pandas data frame and Dask data frame for our data. And then instead of mutating the data, as I was talking about earlier, what we want to do is add a feature. So take the current features we have, and we can see from both of these, we have 50 features. So what they will look like is each column will be var and then the number. So your last column will be var 49. And what I want you to do is write the code here to add a single feature. So that will end up looking like var 50. So that when you run these two cells here, you'll get back your data frame, the pandas data frame in the first one and the Dask data frame in the second one. And they'll be var 0 through var 50 rather than through 49. So I will pause for just a couple minutes to let you guys tackle that. And then I guess I'll answer any questions if anyone has any about that first section. Okay, so look at the solution here. So we create our feature. And what I want to highlight here is this bit of code here is something you'll see pretty frequently when you're designing this way. So this is kind of the other option that you'll end up using as opposed to what we talked about up here with designing these classes that have all this information. And so a lot of what you'll end up doing when things get a little more complicated and you're using different types of data, you'll see these guard clauses, and they're kind of a necessary evil because at least you're keeping everything together. You're staying with the Scikit-learn API. So just kind of wanted to highlight this as like a thing to look out for. And you'll probably end up seeing a lot of this if you're designing in this way. And it's something I would recommend. So just something to keep in mind. And we'll see an example of that later as well. And then so if we run these, we see 51 columns. That's what we expect. Var 0, var 50, great. And then same thing here with the Dask collection. Great. Okay, so then let's do something similar. So we did a transformer. Let's do an estimator. I'm just going to talk through this one, and then I'll let you guys do your own with Dask. So for this estimator, instead of inheriting from transformer like we were doing up here, you can see that we're inheriting from the base estimator. And then what we have here is this custom estimator, the idea here being just to add a logger into whatever estimator you're using. And so any Scikit-learn estimator you can pass in here. Let's see. Yeah, so we'll run that code. And then, again, we'll import XGBoost here. We'll create an instance of that estimator with a few inputs to XGBoost, and then we'll fit our model. And then this one will just show us that we have a trained model. We have our feature importances. And then what I want you to do is to write code like this, but using Dask. So if you look back at the XGBoost notebook, you should be able to do this. So that'll have the information for the changes you need to make this work with Dask. So I'll give folks just a couple minutes to work through that themselves before I talk through it. And again, if you have any questions, please let me know. Okay, so you can see here, the solution is just a few changes. So again, to take this back to the original, the thing we were talking about, our motivation here, for what we're doing at Capital One, this is code that usually our customers or the folks that we work with would write. But depending kind of like what you're developing, if you're developing a library for folks to use, or if you are the folks using that library, the advantage here is to scale with Dask from traditional XGBoost. The only changes you need to make to a custom estimator like this are passing in the Dask XGBoost classifier and passing in Dask data. I do want to highlight, if we go back to look at this estimator, what you'll end up seeing in any case that gets just a little more complicated, if you're doing something else with the data, you'll probably end up seeing the guard clauses like you would or you did in this transformer. So you would see those in the estimator. But we wanted to make a simple example to focus on just the using the correct XGBoost classifier and the Dask data. So then somebody asked earlier about a pipeline with this stuff. So we can do that now. So what we have first is we're just going to drop those last two columns that we added so that we can reuse that same data set and then make sure that the pipeline is running that classifier again. So we've done that, we confirm that. And then this is what our pipeline looks like. So add features doesn't have any initial setup parameters. So we can add that in directly. The custom estimator does because we're giving it the XGBoost classifier. So we just create that variable to make that a little cleaner. And then the other thing I want to call out here is these strings are arbitrary. And we'll come back to those a little later. There's a reason that I'm highlighting them because we'll need to know what they look like in order to access some attributes on the estimator in a little bit. But I'll explain that when we get there. Just wanted to highlight it. Okay, so we've ran our pipeline. We removed that column and now we've added it back. So we know the transformer ran. That's great. And now we see the feature importances again from the custom estimator, not from the estimator we used before. So we know that the pipeline ran that transformer as well. That's great. So again, I'll pause for just a couple minutes to let people try this with Dask to see what the difference is. And if anybody has any questions, please feel free to hop in. Sorry, I'm going a little fast. I just want to try and get through all of this stuff to leave you with something to work on for the future. Okay, so for the pipeline, we can see that we can kind of just combine what we did earlier. So using the custom estimator, just import the Dask XGBoost classifier, and then when we call the pipeline, call it with the Dask data that we created before, and then do the same confirmations we did before, making sure that we've added the feature and that we have our feature importances. There we go. And 50 columns, good to go. And we have our feature importances, great. So then the last thing I want to talk about is somebody asked before about running grid search over these pipelines with Dask. So I'm going to skip ahead past the cross-validator to show the grid search, and then we'll come back to that. So what we have here is a grid search doing exactly that. So this first cell is setting up the data, a new data set here, adding in dates because the cross-validator we're going to use is time-based. Instantiating that cross-validator and calling split on that to get our input for the grid search. And then this is what I was calling out earlier. So let me scroll back up just to highlight. So again, where you see this string for custom estimator in the pipeline, that's how we're going to access the parameters for XGBoost in this params grid. So if you were calling if you were assigning the estimator in grid search as just an estimator, this would be just min child weight. But because we're giving it the pipeline in order to access that parameter and any other XGBoost parameters, you have to give it the name that you've created in the pipeline, then estimator, then the parameter. So just a heads up for any of those. If you want a better model, you should use these parameters, at least to search over. I've skipped them here just so this runs in a reasonable amount of time. And then down here, we give our cross-validator as an input. We give a scoring function. We want a little output, so we make it verbose. And so that's the grid search. That's what we're going to run in a second. I just want to talk quickly about this cross-validator. To get a better idea of the motivation for this, this is the article it was pulled from. But the idea here is we wanted to give a slightly more complicated cross-validator because the things we've built up so far have been relatively straightforward. And so we wanted folks to get a chance to try something with a little bit more complexity. And so the idea for a time-based cross-validator is, first for this, because a lot of the cross-validators that you would use in real life are already implemented in Scikit-learn. So here's one that's not. And the idea here is also in terms of real-world application is sometimes you will have a list of dates that aren't necessarily in order, and you want to split on them, for example, by a given date. So that's what this is doing, a pretty straightforward example of a cross-validator split with dates. And again, dates are always difficult and annoying, so it's a good practice problem to kind of work through. So that's what's going on here. We'll go ahead and run this quickly. And we'll run the grid search. And then what I can tell you ahead of time is what will happen when we try to run this code. This is the boilerplate. It will error when we get to the cross-validator, and that's because we have not extended it to work with Dask. The rest of this should work. We're accessing the Dask estimator that we created for the pipeline. We're accessing the Dask version of the pipeline. But this was the exercise I wanted to leave to you all. What you'll end up having to do is implement some of those guard clauses or refactoring some of the data access here to work with both Dask and with Pandas to be able to implement this. So, and I think if you can solve this, you should feel pretty comfortable with what you've gained here in terms of how to design within the Scikit-learn API, and therefore use Dask-ml as kind of a way to scale the code you're already writing. Okay, I'll stop talking there. I know we're really close to time. I'm happy to answer questions, and if folks want, I can step into the gather space afterwards to talk to folks, or you can message me on the Slack here. But thank you so much for your time, and I'm happy to answer any questions.
Okay, wonderful. Well, this is Nathan, the tutorial host, chiming in. Let's give a big round of applause and thanks to our presenters today for this tutorial. And I'd like to encourage any further discussion or questions to follow up directly with, there you go, I got a clap too, with our wonderful presenters either in Slack or Gather. And also want to encourage everybody right now, there's lightning talks happening. I posted the link in the chat and you've probably been spammed with it a couple other places too. So everybody head over there. Thank you so much.
Thanks, everyone.
Thank you.
Thank you.